Hello, I'm Tanmay Shukla and this is Lab 4 Physics 2211 at Georgia Tech. Introduction. So the objective of this lab was to analyze and model the 2D oscillation of a spring mass system using tracker and glow script. Method was to use tracker to extract the x and y position data from the video, and then modify and run glowscript starter code to simulate the system, and then to compare the observed and predicted motion using and analyze the energy graphs. Key physics principles. Newton's second law of motion, which states that the net force acting on an object equals to the mass times the acceleration of that object. Hooke's law, which says that the F spring equals to K times L minus L naught times L hat, where L is the length of the spring, L naught is the relaxed length of the spring, and L hat is a unit vector in the direction of the spring. Gravitational force, Fg equals to negative mg j hat, where j hat is a unit vector in the positive y direction. Then we have energy conservation, which states that the energy total equals to K plus the potential energy to gravity plus potential energy to the spring. Kinetic energy is equals to half mv squared. Gravitational potential energy is equals to mg y, where y is the displacement in the y direction, and spring potential energy, which equals to half K L minus L naught squared. Experiment setup and initial data. To calibrate, we use known reference length from the video. The origin was placed suspension point of the string as described in the lab, and the positive y direction pointing upward or downward depending on video conventions. Initial data from the video for setting up the glowscript model. The mass was 0.402 kg, spring constant was 6.843 newtons per meter, relaxed spring length was 1.123 meters, and frame rate is 30 fps, or the time step used in the lab was 1 over 210 seconds. This is the tracker video. Experiment data. So from the data and tracker, we can get the initial position and velocity for the glowscript model. So the initial position is negative 0.0409, comma negative 0.687, comma 0. And the initial velocity was calculated by using the first position data that we have for both x and y. The glowscript initial conditions is the same as discussed previously, G, Ks, and L naught, and the L is equals, so we initialize the length of the spring as the position of the ball mass position of the spring. L hat is a unit vector, so we divide L by the magnitude of L, and S, which is displacement, is just the magnitude of L minus L naught. That is how far is the spring from the relaxed length. We then initialize kinetic energy, gravitational potential energy, spring potential energy, and E as shown. This is the calculation loop. We update the F grav, F spring, F net, the velocity and position with the velocity and position update formula respectively, and the length of the spring, the unit vector of the spring, and the S, as you can see, and we graph it. Here's the result. So this is change in energy versus time. You can see that delta K, delta U, grav, and delta U spring all oscillate harmonically as expected, and delta E, as expected, as it should be, is along the x-axis where the change in energy is 0, and that conforms with the energy principle. This is the glowscript observer change in x position with time. We can see that the experiment is pretty close to the glowscript model, similarly with y. And now we come to sources of error. So one source of error could be tracking accuracy in tracker. Maybe the manual point placement can lead to small errors in position, especially if the mass is blurry, spinning, or moving quickly. There could be a calibration error, inaccurate calibration stick placement, or incorrect reference length. Tracker can scale all measurements incorrectly. Frame rate limitations is capped at 30 fps, so something very fast may not be resolved smoothly and could cause jumps or underestimation of velocity. Is a numerical approximation in glowscript. A finite time step in solution can introduce small energy drift over time. Um, Now there's a discussion questions associated with this lab. The first question asks, for your model system, is the energy principle satisfied? Justify your answer by discussing briefly your plots of energy changes. Yes, actually the energy principle is satisfied in the model system. So if you look at the plots in the previous slides, as I discussed, here delta E, which represents the total change in energy, that is change the sum of the change in the sum of all the energies here, it's 0, which confirms the energy principle that states that energy cannot be created nor destroyed, so the change in energy must be 0. So yes, it is satisfied. Second question asks us, if using the data we obtain in tracker, make two separate estimates of oscillation periods, first by estimating the period of oscillation from the x position data, and second from the y position data. So using the plot obtained, we estimate the following two oscillations periods. So in the x position, using the x position data, we received an oscillation period of 1.615 seconds, and using the Y position data, we get an oscillation period of 1.519 seconds. Periods are very close with a slight difference of about 0.096 seconds. The small discrepancy is expected due to couple nature to spring's motion in two dimensions, or slight phase shifts between vertical and horizontal components. That's it. Thank you. This is Tanmay Shukla signing off.